my channel. I'm going to discuss today a very important topic, which is a part of chemical bonding and periodic classification. It is a part of both the chapters, and this is Fajan's rule. So I'll be discussing Fajan's rule and almost all applied questions that can be asked related to this particular topic for your CBSE class 11th exams, class 12th boards, as well as JEE and NEET. So this is going to be helpful for all kinds of exams. A general topic, Fajan's rule, which helps us to decide the percentage of covalent character in an ionic compound. So let us proceed quickly. Yeah. So to begin with, I'm going to discuss what is the difference between an ionic and covalent compound. So in brief, you need to understand when the electronegativity difference between two combining atoms is very large, they tend to form an ionic compound. So in an ionic compound, an intact, a proper normal cation gets attracted towards an anion, and an electrostatic force of attraction. Electrostatic force of attraction holds the cation and anion together, and that is what we call as an ionic bond. Now, when does an ionic compound have some percentage of covalent character? When this cation is small in size and this anion is large in size. Now, a small cation means its nucleus will have a strong attractive pull on the electron cloud of any neighboring species. And a large anion means its electron cloud can be easily distorted, right? So what does this small cation do? This small cation is polarizing in nature. Polarizing in nature means it can polarize the large anion. That means it can deviate its electron cloud. Electron cloud originally was symmetrical, and now, since this is a small cation, it tends to pull the electron cloud of the neighboring atom towards itself, distorting its symmetrical electron cloud and creating two oppositely charged ends, the partial negative and the partial positive. So this ion is easily polarizable, and this is polarizing. For a cation to be polarizing, it should be small in size, and for an anion to be polarizable, it should be large in size. As a result of which, this end becomes partial negative, this becomes partial positive, and there's some kind of overlapping between the two species, which brings in covalent character in this molecule. Now, what does Fajan's rule do? Fajan's rule is going to help us for qualitative determination of percentage of covalent character in an ionic bond. Qualitative determination means it's not going to tell us exact percentage, but it will tell us whether it's more covalent or more ionic. And we need to understand no bond is 100% ionic or 100% covalent. Every ionic bond will have some percentage of covalent character, and every covalent compound is going to have some percentage of ionic character. How to decide which is more covalent, more ionic, that is what we're going to learn. Now, understand a polarizing cation is a small cation, a cation with high charge, or a cation with pseudo-noble gas configuration, which is also called as a supercation. Normal cations have noble gas configuration, but if a cation has pseudo-noble gas configuration, it is also called as a supercation. It becomes more polarizing. Now, more polarizing also means more charge to radius ratio. This is charge to radius ratio. So if the charge is high and radius is small, small radius and large charge is large polarizing power, right? So a polarizable anion is the one which is large in size and has a high charge. So the point to be noted here is both cation and anion should have a high charge for more percentage of covalent character. Now, in general, if I'm talking about a sodium ion or a magnesium ion, higher, or let us say if I just take up two ions with the same charge, two similar ions having a different charge, Mg1 plus and Mg2 plus. So Mg1 plus is going to be larger in size than Mg2 plus, obviously. How do we decide that? We have 12 protons because Z in magnesium is 12, and this is having 1 electron less, means 11 electrons. In this case, 12 protons, because protons are a part of the nucleus. They do not change during any kind of chemical change. So Z is 12 protons and electrons here are 10. So 12 protons pulling 10 electrons will lead to a smaller size than 12 protons pulling 11 electrons. So in this case, Z effective is more. Z effective is more in this case. As a result, Mg2 plus is smaller in size than Mg1 plus. Similarly, if I talk of O negative and O2 negative, in this case, Z of oxygen is 8, means oxygen has 8 protons, but in O1 negative, there are 9 electrons and here there are 10 electrons. So 8 protons pulling 9 electrons or 8 protons pulling 10 electrons. So Z effective here is less, which means the size is large. So more the negative charge, larger the size, and more the positive charge, smaller the size. Hence, small cation, high charge will also make the size of cation small, and large anion and high charge, because high charge on an anion, on a negative ion, will make it larger in size. Right? So in brief, if I tell you Mg1 plus and Mg2 plus, we understand Mg2 plus is smaller in size. And if I compare O minus and O2 minus, I understand that O2 minus is larger in size. So we need large anion and we need a small cation. A small cation will more strongly pull the electron cloud of a negative neighboring anion. So small cation, high charge makes a cation more polarizing, and large anion, high charge means the electron cloud is more easily distorted. So it is more easily polarizable. So these are the main characteristic points that will help us to decide percentage of covalent character. These particular features are going to decide more covalent character. So more covalent character is observed if we have small cation, large anion, high charge on both, and pseudo-noble gas configuration of the cation. Now let us observe a few examples and understand. The first case I'm taking up sodium chloride and copper chloride. We want to compare sodium chloride and copper chloride. Sodium ion has a noble gas configuration. Now, what is the configuration of sodium ion? Sodium is 1s2, 2s2, 2p6, 3s1. And sodium ion is 1s2, 2s2, 2p6. Just for helping you recall, we have done in periodic that an electron is always lost from the highest principal quantum number while making an ion. So when you make an ion of sodium, the last electron will be removed. We get this as 1s2, 2s2, 2p6, means 8 electrons in the outermost shell. So this is the normal noble gas configuration. But for copper, Z is 29. This is the configuration of copper, 4s1, 3d10. And copper 1 plus ion means highest quantum number, 4. 4s1, we remove the electron. We are left with this configuration. And 3s2, 3p6, 3d10. That is the outermost shell, the third shell, having 18 electrons. This is called pseudo noble gas configuration. This is also a stable, fully filled configuration like noble gas, but this is pseudo noble gas because it has 18 electrons in its outermost shell. And presence of these d electrons due to ineffective screening lead to more Z effective. More Z effective. Why? Because of ineffective screening of d electrons, and hence the size becomes small. So Cu1 plus has a small size, which means more percentage of covalent character. So sodium chloride is ionic, copper chloride is more covalent, chloride is the common ion. So we are going to compare between sodium ion and copper ion, where sodium ion is noble gas configuration, copper ion is pseudo noble gas configuration, hence copper chloride is going to be more covalent. Now, similar examples will be applicable to copper ion, silver ion, gold ion, zinc 2 plus ion, cadmium 2 plus ion, and mercury 2 plus ion. All these ions are going to have pseudo noble gas configuration. So you can just remember any of these: CuCl, AgCl, AuCl, ZnCl2, CdCl2, AgCl2, all these are going to have more percentage of covalent character because they have pseudo noble gas configuration. Now, next we have examples of some compounds, more ionic, more covalent. Now, first pair is sodium chloride and lithium chloride. Here, chloride is same. Lithium being a small cation, this is more covalent. Then sodium chloride, sodium bromide, this time sodium is same. So out of chloride and bromide, bromide being a large anion, this is more covalent. Why? Because for more covalent, we just talked of the points are small cation. These are the points we're going to look for. Large anion and then high charge on both cation or anion, and then pseudo noble gas. So all these points are going to make us compound more covalent. Now, sodium chloride, magnesium chloride, this time chloride is common. So out of sodium and magnesium, we know sodium is 1 plus and magnesium is 2 plus. So due to high charge, this is more covalent. Now, magnesium fluoride and magnesium nitride, both are magnesium. This is F negative. This is N3 negative. High charge is going to make this more covalent, right? That's how you're going to compare. And now, if I just summarize what we have talked, covalent upon ionic is directly proportional to charge, proportional to anion to cation size. How do you read this? This is like an outcome, a summary, a memory aid. Covalent character is directly proportional to charge. Which charge? Both charge on cation as well as charge on anion, which means large cationic charge and large anionic charge means more covalent character, and covalent character is also directly proportional to anionic size, means more anionic size is more covalent character. Similarly, ionic nature is proportional to cation size. That means larger cation size is more ionic nature. This is like a summary of what we've just discussed. Now, more percentage of ionic character also decides these properties. Higher is the ionic character, higher will be the melting point, higher will be the solubility, higher will be the thermal stability. Because more percentage of ionic character means stronger electrostatic forces. Stronger electrostatic forces, which is going to make the compound thermally more stable. Also, more percentage of ionic character would mean more polarity and hence more solubility. And again, more percentage of ionic character means strong electrostatic forces and therefore more melting point. Just remember all these, each of these points is very important from examination point of view, from your MCQ's point of view. So just do it well. And next we have Some more examples depicting the points we've just discussed. This side we have more ionic and more covalent. And let us say I'm comparing sodium chloride and aluminium bromide. Sodium ion and this is aluminium ion. That means a smaller cation with a high charge. And here we have chloride and bromide. This is a large anion, small cation, large anion, more covalent character. Hence, if I ask you which has a higher melting point out of sodium chloride and aluminium bromide, we would say sodium chloride. Which has a higher solubility? Again, sodium chloride. Similarly, barium chloride and beryllium chloride, this is a smaller cation. So, this is going to be more ionic, more melting point, higher solubility. Calcium fluoride, calcium chloride, calcium is common. So, chloride is larger, so more covalent. So, calcium fluoride is going to have more ionic, higher melting point, and higher solubility. Similarly, out of these two, magnesium is common, and nitride having a higher negative charge is going to have more percentage of covalent character. So magnesium fluoride, beryllium fluoride, this is a smaller cation. This is pseudo noble gas. And out of silver oxide and silver sulfide, this is O2 negative. This is S2 negative, larger anion, more covalent character. Fine. So you can be asked based on more ionic or covalent, higher melting point, higher solubility. Any of these points can be asked. And then the next point is, what else do we relate? Color. You have to remember, children, more covalent character relates to more color. Most of the times, more is the percentage of covalent character, more or deeper color is observed. Why do we observe this color? Because electrons, they are excited, and when they come back to the ground state, they give off transition emissions in visible region. And that is why these compounds show color. So if we compare ferrous hydroxide and ferric hydroxide, this is +3, this is +2. Higher positive charge, smaller size means more covalent, and this is more ionic. Now, more covalent means a deeper color. This is reddish brown. This is either pale green or colorless. This is a deeper color because of more covalent character. Similarly, this being more covalent is less soluble, whereas more ionic is more soluble. And that is why ferrous hydroxide is more soluble, whereas ferric hydroxide tends to precipitate out. Now, if I compare lead chloride and lead iodide, lead chloride is white, lead iodide is yellow. Lead is common. Out of chloride and iodide, iodide is larger in size, more covalent, so more colored, right? And then a very important observation and comparison is amongst the silver halides. Remember, if we compare AgF to AgI, I negative, largest size anion, and cation is the same in all these. So largest anion means most covalent, means the brightest in color. This is most ionic and this is colorless. So that's how the color varies. AgF is colorless, AgCl white, AgBr pale yellow, and AgI is proper yellow. Each of these are important questions. The next one we have is thermal stability. More percentage of ionic character also accounts for high thermal stability. How do we compare? If I compare sodium carbonate with magnesium carbonate, magnesium with smaller cation, more charge, has more covalent character. So sodium carbonate is thermally more stable than magnesium carbonate. When you do this as part of periodic, we also study it this way, that carbonate is a large anion, so larger cations can stabilize larger anions. And since carbonate is a large anion, and out of sodium ion and magnesium ion, sodium ion is larger in size. So sodium carbonate is more stable than magnesium carbonate. Or in other words, magnesium carbonate has more covalent character. That is why it's less thermally stable than sodium carbonate. Similarly, if we compare magnesium carbonate with beryllium carbonate, same point, beryllium smaller cation, more covalent. So magnesium carbonate is thermally more stable. Another point that we have here, this is also a very important question asked in so many previous year questions. Why is SnCl2 a solid but SnCl4 a volatile liquid? So how do we compare? SnCl2 means tin and plus 2 oxidation state. Here tin and plus 4 oxidation state. Higher positive charge means a smaller cation, and smaller cation means more covalent, and more covalent means lesser melting point because ionic compounds have more melting point. Lesser melting point means it is going to have its physical state as liquid and a volatile liquid. Whereas SnCl2 is going to be more ionic, which means stronger forces, which means higher melting point and hence a solid at room temperature. So I hope this helps, children. If you like this and this concept helps you, please do like, share, and subscribe. And in case you like the video, you like the way this is presented, please comment. And you want any changes, please feel free to comment and share. Thank you. God bless you all.